Today is December 20th, 2022. This is my 167th episode for C++ 17 2023 CUDA SQL OpenCL TBB Vulkan. Implicitly defined functions, derivatives of higher order 3. We will learn n variable derivatives and function generator. If you want to follow my current session, you probably have to watch my previous episode 166, implicitly defined function derivative of higher order 2 first order derivatives. Please double click this link. If you haven't watched my previous video, episode 166, first order derivative, you may not be able to follow my current session. Download the current video source code. Show in folder, extract, rename 167. Copy, paste it in your working directory. Open up Visual Studio Code. From the folder 167, open up holiness.hpp, newton.cpp, Ctrl B. I will arrange side by side. Control Home, Control Home. I assume you have watched my previous video listed here. In our previous episode, we implemented implicit derivative first order. Up to this point, we played games with two variables. Now we generalize. In practical application, we need three variables x, y, z, or four variables x, y, z, and t, or five variables. So we have to generalize this algorithm. Now scroll down. Please understand, when we use two variables, x can be unknown or y can be unknown. If we have three variables, we can copy, paste. Then it can be z unknown. But what about 5 variables or 6 variables? We cannot extend our algorithm this way. I will delete this part. Now observe. In case of variable x is unknown, we solve the equation for x. So the value xx is solved. In case y is unknown, we solve the equation for y. In this case, y is unknown. We evaluate the values of y, then we put the evaluated value here. In case x is unknown, we solve the equation for x. Then we put the value x here, the evaluated value x here. So this part can be generalized. Also, in this case, the return value would be x, y, and derivative. What about if we are using three variables? Then the coordinate becomes x, y, z, and the derivative becomes, for example, dz over dx. Also, dz over dy. So this represents coordinates. This represents derivatives. If we use, for example, 4 variables, then coordinate becomes s, x, y, z coordinates. Then derivative becomes dz over ds, dz over dx, dz over dy. This is derivatives. You have to understand this point. Now copy from here up to this point. Copy, paste. Scroll up. We will rename first order generalized. We will introduce type name ARG types. This is plural. So ARG types, ARGs. Delete this part. Now we will use constraint. ARG type should be arithmetic type. So CPT arithmetic C 와 control home namespace CPT CPG types control end. Scroll up. Then we have to make ARG type to be identical. I think I made typo here. Arithmetic. I made typo. Then we make all types of ARG types identical to ARG type by using SED same as ARG type. We use type constraints. We made ARG type support addition, subtraction, multiplication, etc. by using arithmetic C. Also, we made all types of ARG types to be the same type with ARG type. Now, here the element count of coordinates should be convex per or ARG count, size of ARG types. Okay, if ARG count is, for example, is 3, then the element count of derivatives becomes ARG count minus 1. Please observe, coordinates are computed using extended Newton method. Okay, coordinates are computed using this function. So it should be ARGs. Also note that derivatives are computed using implicit derivative. using this function. Here, using code T SCD array, element type should be ARG type. The element count of coordinates should be ARG count for coordinates. Now, using derivative T, this derivative is computed using this function. We pass ARGs. Its return type is Dagger type. This is compile time programming. Or we can say this type is effectively equal to STD array ARG type. Then ARG count -1. So this type is actually equal to SCD array ARG type ARG count -1. Now we defined coordinate type, derivative type. Then this element should be modified. STD tuple coordinate T derivative T. Okay. Now in this part, copy this, then paste it here, an indent. We have to call this function by passing arguments, but we cannot call this way. Instead, we have to use std apply. Here, we define auto di ff. We capture f. Then auto values semicolon return. We call this function indirectly by passing values. Of course, this function comes from our function call arguments. Also, dependent index is used here. With this, we can use auto df std apply. We pass di ff. We have to pass either tuple or array. Either tuple or array. simpler. Now I define SCD array coordinates should be ARGs. Okay, we create coordinates like this, but this coordinate should be updated for this part. We can update like this: SCD get var idx coord equals this solution. So cut, paste. We handled this part here. Now we don't need this because we handled here. We called this function defined here. So implicit derivative is called through this function. We have to pass coordinates. I say coordinates. This coordinates is expanded for values and passed to this function. This coordinates is passed to here. Then we have done. Element T is tuple. Instead of doing this, we can use CPT make tuple. This is a function. The first comes coordinates. Second comes df. This is derivatives. Okay. Then we don't need this part. We implemented all these parts. Scroll up like this. Now this function supports arbitrary number of variables or arguments. With this, we can now play games. Functions such as a times x square plus b times y square plus c times z square equals, for example, 25. We can now play games against 1, 2, 3 variable function. Now copy from here up to this point. Paste it. We can delete up to this point. I will rename generalized function. We can also delete this part. I will make it clean like this. We have to delete this part. Here, return, we capture all by value. Then we can use reference F. We use angle bracket, STD, same as. We can use this ARG type. Then ARG types, parentheses, ARG types, ARGs. Now we call this function. We pass var index, dependent index, I would say IDX. Then we pass split count. Then this range. Then this function ARGs. Of course, we have to return. Don't miss semicolon. I will explain how to use this function shortly. We will use this function to implement second order implicit derivatives in my next episode. With this, Control N. We will copy this function up to this point. Copy, paste. Scroll up. We will change the name Generalized. We don't need to change anything, but I will modify this part. Now it is generalized. We are calling our new function implemented here. Now in this part, we also have to make changes. This derivative returns vector of type element t. This element t is tuple. So the type of t is LT, defined here, or cos, also derivative dy dx d. We extracted cos t derivative t from d. Then or xx yy cos or I say this is df. Okay, df's type is derivative t. This derivative t is SCD array. So we say dx dy is df. Or we can say derivative because we use the plural here. We can paste it like this. I will delete auto. Then the remainder is the same. Now copy this function, Ctrl N. We will paste it here and disable it. We will try any compiler. I will use Intel compiler. dir cd 167 Newton dp cpp version. Now it complains dp cpp is deprecated and will be removed in the future release. Use icpx fcycle. So icpx SED C++ training fno cycle newton.cpp oi.exe. Hit enter. I would copy this command string, copy, Control Home, paste it here. Now cls dir I. We found two sets of solutions. In this case, Ctrl N. This is the problem. X is 4. X is 4 given. Then we found one solution for y. X is 4, another solution for y. We found derivative at this point. We found derivative at this point. So when x is given, we found one coordinates, two coordinates, then derivative at each point. Derivative at each point. Algebraic solution matches with our numerical derivative. Now your homework is this. Try x squared 2 plus y squared 2 plus z squared 2, for example 25. Find first order derivative in this sphere. Now we will test this function, implicit derivative first order generalized function. We will use this function in my next episode to implement second order derivative. Now copy this, paste it here. I will delete this and change the function name. function. Then copy this, Control and paste it here. Disable it. I will explain how to use this function. Now we don't need this. Then auto get derivatives. Now we are calling this function. Copy, paste. We pass solve for y and dependent y. Then we pass this argument here. We don't need xy. Okay, we don't need xy. I will give line break here. Xy is missing. This is function. Okay, I will change it unknown y. In this file, control home, we defined y unknown, so I renamed unknown y. Now here, auto derivative. We call this function. Please understand. Implicit derivative, first order generalized function, returns a lambda. This lambda takes ARG types ARGs. Okay, so we pass x and the unknown y. We can change the value of x arbitrarily. Once again, we can change the value of x arbitrarily. Then this function works. We don't need to specify these things repeatedly. We don't. We can simply change the value of x. With this, I will rebuild. This is Clang compiler. CLSC. So Clang compiler gives the exact same solution. We can try with Intel compiler. CLSI. So both Clang and the new Intel compiler works correctly. I will copy this command string for your reference. We can also try Microsoft compiler. dir cd 167 Newton CL EHSC SDD C++ 20 Newton.cpp fe m.exe. Hit enter. Please note I have code page warning. Anyway, it built. Here, double click it. Save with encoding. UTF-8 with a bomb. If we build again, it won't complain. CLSM. So I will also copy this command string and paste it here. Control End. As I said, this is your homework. Please understand. I will copy this, paste it here. Suppose we are solving such problem when x is 5, y equals 0, dy dx is either infinity or negative infinity. We can handle such things, so don't worry if you face infinity at certain points, okay? But try to solve this equation for first order derivative, such as dz over dx, dz over dy, or dx over dz, dx over dy. You should be able to evaluate all these things if you understand and followed my instructions carefully.